All right, so we are getting to where we're going to graph some more complicated functions. So these are going to be the ones that have sines and cosines in them. And I have given you all a polar graphs discovery sheet that I want you to use with a graphing calculator. I want you to put your graphing calculator in polar mode, and I want you to just type the equations into the calculator and get your window set and press graph, and then just sketch them on the discovery handout. And then you're supposed to figure out characteristics of the different graphs. Because when I look at this, I already know what this should look like because I know the characteristics of what this graph is. If you don't, then you're just depending on doing theta and figuring out what R is by plugging theta in here, which is what I'm going to show you how to do. But I want us to know a little bit more about the graphs and know their patterns. And so that's what this discovery handout is for, is if we know the patterns, we'll be able to graph things quicker because we're doing calculus. We're not learning how to graph polar functions. That's not going to be tested on the AP exam. We've got to do the calculus part. So this is just understanding the polar graphs because we need to be able to do the calculus. All right. So again, you're not going to be asked to graph a polar graph on the AP exam. You're going to be doing calculus with them, but you've got to know about the graphs to be able to do that. All right, and know about the patterns and their periods and stuff like that. So if I'm doing this by hand, just remotely by hand, I'm going to pick values of theta. So I'm going to do like 0, I might do pi over 4, I might even do pi over 3, and then do pi over 2, and then maybe 3 pi over 4, and then maybe pi, just picking some values of theta. All right, so then I substitute in. Cosine of 0 is 1, 1 times 2 is 2. Pi over 4, the cosine of pi over 4 is radical 2 over 2. Then I'm going to times by 2, so that gives me radical 2, which is 1.4. Okay? So that one's 1.4. Then I'm going to put radical 3, pi over 3 in here. So the cosine of pi over 3 is a half, and then 1/2 times 2 is going to give me 1. And then pi over 2, the cosine of pi over 2 is 0, so of course 0 times 2 is 0. 3 pi over 4, the cosine is negative radical 2 over 2. And then I'm timesing that by 2, so that's going to give me negative radical 2, which is negative 1.4. And then when I put pi in here, that's negative 1. So negative 1 times 2 is negative 2. And then I'm going to go over here and graph this. So at 0, 0 on the polar graph, just like doing the unit circle, 0 for theta, and then I'm on this axis, I'm going to go out 2 units to the second circle. So 2 units at 0 degrees. Then I'm going to go to pi over 4, which pi over 4 is going to be in the center here. And I'm going to go to 1.5. So I'm going to do 1.4 rings. So I'm about right here. Then I'm going to go to pi over 3, which this one is pi over 3. I'm going to go out 1 ring. And then I'm going to do pi over 2. So pi over 2 is this one. But I'm at 0, so I'm at the pole right here. And then 3 pi over 4. So 3 pi over 4 is the middle of the second quadrant, 3 pi over 4. But this is the positive end of it. I need to be at negative 1.4. So that means I'm over here on this side at 1.4. So I'm right here. Whoops. Come on, pen. 1.4 is right there. So about 1.5. And then at pi, which pi is right here, but this is the positive end of the axis, I need to be at negative 2. So negative 2 is going to be on this side, which puts me back at that beginning point where I started. So what did I do? I just went in a circle around here. Now, I already know that this is a circle because I know the pattern of this function. So anytime I see a function that's r equals some number times cosine theta, I know that's a circle. The 2 tells me the diameter. So the diameter of this circle is 2 across. And because it's cosine, it's symmetrical on the x-axis here. If this was a sine, it would be symmetrical on the y-axis. So it would be up here. So I already knew that graphing. So if you know the patterns about the different functions, then that will help you to graph these so much easier. Okay? All right. Now, what I want to do for this same problem is I want us to come up with the Cartesian equation for that same graph I just drew. So I want the equation of that circle. So how do I use my polar stuff to convert this equation into a Cartesian equation? Well, you're just going to substitute in your equations. Well, one of the equations we know is the Pythagorean theorem one. R squared is x squared plus y squared. All right, that's your equation of a circle centered at the origin. All right, using that Pythagorean theorem. All right, so if that's r squared, then r is going to be the square root of x squared plus y squared. And then this is 2 times cosine. Well, how am I going to get the cosine? Well, I know the x coordinate is r times cosine. Okay, so the cosine is going to equal x divided by r. Okay, so the cosine is x divided by r. Now, I already know that the r again is the square root. So I've got the square root of x squared plus y squared equals 2x divided by the square root of x squared plus y squared. So now I just multiply this guy over here. So a radical times a radical is going to give me this expression without the radical equals 2x. So there you go. You have that equation in x's and y's. Now we can complete the square and figure out where the center is, because that's what it says for us to do next. So if I move my 2x over, I'll have x squared minus 2x, and then I'm going to leave a space to complete the square, plus y squared equals 0. So how do we complete the square that you learned in Algebra 2? That's where you take half of the middle term and then square it. So half of this is -1. Square that will be +1. And I added both sides. This is now a perfect square that we just created. So this quantity here is now a perfect square. This is x minus 1, quantity squared, plus y squared equals 1. So there's the equation of a circle. And we know a circle's equation is x minus h squared plus y minus k squared equals the radius squared. So comparing this equation to the equation, standard equation of circle, the h and the k is your center. So that means my center is at 1, 0. All right, my center is at 1, 0. And then we know it's equal to the radius squared. So the radius squared is 1, so that means my radius is 1. So I know from this equation that we just calculated that this is a circle centered at 1, 0 with a radius of 1. Well, let's go back and look at our picture. Here's our center at 1, 0 with a radius of 1. So this circle has a center. If I think of this as the y and the x-axis using Cartesian coordinates, the center is at 1, 0, and it has a radius of 1. And that's exactly what that circle is. So in order to solve this for y, of course, you would move this over to the other side. 1 minus x minus 1 squared, and then you would take the square root. So you'd get y equals the positive and the negative, because when you take a square root, you get both a plus and a minus of the quantity square root 1 minus x minus 1 squared. So this is 2 equations. It's 2 equations because the graphing calculator, when you put this in your graphing calculator, excuse me, in your rectangular mode, in your normal mode, you have to put in y1 the positive equation so that it graphs the top of the circle. Then in y2, you have to put the negative square root so that it graphs the bottom of the circle. Because a graphing calculator only graphs functions, so when it graphs circles, it can only graph the top half and then the bottom half. So the top half is the positive half, the bottom half is your negative half. And so that's these 2 equations is your top and your bottom of a circle in rectangular mode. Okay, if you are in polar mode, all you got to do is type in this equation, r equals 2 cosine theta, in polar mode, and it'll graph that same circle. So it just depends on what mode you're in, what equation you're going to put in. All right, so that is the equation of the circle with center at 1, 0 with a radius of 1, which is exactly what we graphed when we graphed r equals 2 cosine theta. All right, so the next 2 I want us to graph. And this is just another way, instead of doing a table, this is just another way to organize your thoughts. First, sketch r equals 1 plus sine theta. Sketch it as a Cartesian first, where it's got an x and a y axis. So I graph theta on one axis and graph the R on the y-axis, on the vertical axis. So I'm just graphing the sine curve shifted up 1 unit. Well, that's exactly what this is. The sine curve is, of course, this, right? There's your sine curve. It's at 0, then it's at 1, then it's at 0, then it's at -1, then it's at 0. But then it was shifted up 1 unit, right? Everybody was shifted up 1 unit, so now I'm up here, okay? So I have just basically just graphed this function with theta on the x-axis and the r on the y-axis. So this is graphing it in like Cartesian first. So what I want to do is come over here and graph it on the polar grid now to make it a little easier. So for 0, I'm going to graph 1 unit. So at 0 radians, I'm going to come out 1 unit and be on the first ring. At pi over 2, I'm going to come out to 2. So at pi over 2 right here, I'm going to come out to the second ring. I missed. There we go, the second ring. All right, for pi, I'm going to come out to the first ring again. So over here on pi, I'm going to graph out to the first ring again. For 3 pi over 2, which is down here at the bottom, for 3 pi over 2, I'm going to graph, stay at the pole at 0. And then for 2 pi, I'm at 1 again. So when I come back around to 2 pi, I'm at 1 again on the first ring. Now, I know that's only 4 points. So what the heck does this look like, right? What does it look like? So if you know about the graphs, which again goes back to that discovery handout sheet that I'm talking about, if we go through and do the discovery sheet and understand about all the different, the lemniscates and the limesons and the cardioids and the roses and all the circles, there's names for everything, and the graph, the equation of those functions have a consistent pattern. So when you're looking at this, this is 1 plus 1 times sine theta. All right. This is actually a cardioid. This is a cardioid. All right. This is a cardioid. And this is A plus B sine theta. All right. Now, a cardioid looks like a heart, but it's rounded, so it doesn't have a pointed end. So a cardioid looks like this. It looks like a heart. That was a bad graph. Let me try again. That's a little better. All right, so it looks like a heart, but it doesn't come to a point on the end. Now, some of them have a little loop on the inside. These are called limesons. All right, limesons. And it's got the little hook on it. It's a French word. All right, but if it's got a loop inside, it's called a limason. If it doesn't have a loop inside, it's called a cardioid. So these are the words or the things that you're gonna, we're gonna go through on that discovery handout and be able to think about what the patterns look like at all. All right, if the A and the B are equal, then you know it's a cardioid. It doesn't have a loop. If the B number is bigger than the A number, then it's a limason. All right. Now, the A and the B number tell me a little bit about this graph. All right, the A number is how far out this goes on either side from the little pinched in piece. All right, so I know this cardioid goes out 1 unit on either side of where it dimples in. Then the length here is your A plus your B. So A plus B. So I know this is going to be a length of 2, and these are going to be lengths of 1 on either side. So looking at this picture I have right here, I know that this is going to look like this. Okay, so I go out 1 unit. Let's see, I'm not quite symmetrical on that side. Let me make it a little more. There we go. It goes out 1 unit on each side, and its depth here is 2 units. So that came from the A and the B. So my length here out is the A plus B, and the length that it goes out on either side here is the A value. Okay, so, and that's when you do a cardioid. All right, now if it has a loop in it, then that's going to be the B minus the A. So since these are equal, B minus A is 0. That means it doesn't have a loop on the inside. But if the B number is bigger than the A number, when you do B minus A, it'll tell you how long this little loop is on the inside. All right. All right. So that's just a little bit about that, and we'll talk about that more when we do our discovery handout. All right, but for right now, we just want to kind of have an idea of if you do this graph first, then it makes it a little easier to convert it and come over here and do it. But it's going to be nice to know what these graphs look like, okay, to kind of have an idea before you graph it. So it makes graphing a little easier. All right, and the last one we want to look at here, it says sketch this curve, r equals cosine 2 theta. Now, something happens when you have a number in front of your theta. All right, r equals cosine 2 theta. This is when you graphed, this is the b number when you graphed in pre-cal. All right, don't get that confused with the b number here that's in front of the sign, because when we're doing the cardioids and things, this r equals a plus b. Okay, that's where our b is going to be. But for this one, when I'm thinking about the period here, this b number here from the period is the number in front of the theta sign. All right, so don't get that confused with our other b number that we're doing in the polar stuff. So this goes back to pre-calculus. So to find the period of this graph, of this cosine graph, it's 2 pi divided by this number in front of the theta. So 2 pi divided by 2 is pi. So when I graph this down here, this is going to go through 2 cycles going from 0 to 2 pi. It's going to go through 2 cycles, and you'll see here in just a minute. All right, so if we do our graph here from 0 to 2 pi, and we plug them in, we're going to put 0 in here. The cosine of 0 is 1. So I'm going to start up here at 1. Then I'm going to do pi over 2. So pi over 2 times 2 is pi, and the cosine of pi is negative 1. So that puts me down here already. Now, if I did pi over 4 right here, if I put pi over 4 in there, pi over 4 times 2 is pi over 2, and the cosine of pi over 2 is 0. All right? And so if you know what your cosine curves looks like, you know it's going to look like this, right? And I can just keep on filling it in. If you didn't, you could just plug those numbers in here and just work it out. So we know our cosine looks like this, right? Just like the sine curve, except it starts up here at 1 when you're at the origin. Starts at 1, where the sine starts at the origin. All right, so notice this went through 1 period, 2 periods. So this went through 1 cycle, 1 period cycle from 0 to pi, and that's why I did the 2 pi divided by this 2 right here. So what that does is that shortens your period to just 0 to 2 pi instead of 0 to pi instead of 0 to 2 pi. All right, so how do I graph this over here? All right, so let's take these points and look at what goes on here. So at 0, I'm at 1, and this is going to be really, really small. I apologize. I should have blown this up a little bit to make it a little easier to graph. But 0 is 1, so at 0, I'm going to be out at 1 on the first ring. Then when I'm at pi over 4, I'm at 0. So pi over 4 here is in the center right here, pi over 4. But I'm going to be at the origin. So there I am already at the origin. Okay. Then when I'm at pi over 2, so pi over 2 is up here. At pi over 2, I'm going to be at negative 1. So I can't be on this positive end of the graph. I'm going to be at negative 1 down here. Okay. So here's what's happening with this picture. All right. It's going from here. Okay, pen, you got to be nice to me because this is small. All right. I'm going from here to here, down to here. All right, that's where I'm going so far. Now, so then I'm going to do 3 pi over 4. I'm at 0 again, so we come back. So then when I'm doing 3 pi over 4 here, I'm at 0 again. So this shifts up to 0. And then at pi, so at pi, I'm going to be at 1. So I'm going to be at 1. So that shifts around to here. And then when I'm here between pi and 3 pi over 2, which is going to be right here in the middle of this quadrant, I'm at 0 again. So that pulls in there again. And then at 3 pi over 2, I'm at negative 1. So remember, this is the positive end out here. So at 3 pi over 2, I'm going to be at negative 1, which puts me out here. So I just came in here. So now I'm up there. And then at this 5 power 4, I'm going to be at 7 power 4. At 7 power 4 right here, I'm going to be at 0 again. So that pulls me in here to the 0 again when I'm on this one. And when I'm back to 2 pi, which I'm back to 2 pi here, I'm going to be at 1. So that's going to pull me around back to here again. All right, now notice what we got. We got a 4-leaf rose. So to me, it's harder to graph it this way. That's why that discovery handout is going to be so much easier when you look at the patterns and everything that's going on, all right? Because if you know your patterns, when you get this equation right here, r equals cosine and then a number in front of your theta, you already know this is a rose petal. Just because it has this number in front of your theta, cosine 2 theta, all right? Now, since this is an even number, that means my number of rose petals is going to be double. So that's why we have 4 petals. When this is an odd number, that's how many petals you have. So if this had been cosine of 3 theta, then I would only have 3 petals. So when this is an odd number, that's how many petals I have. But when it's an even number, you have double the number of petals. So if this was cosine 4 pi, there'd be cosine 4 theta, there would be 8 petals. It would be an 8-petaled rose. All right, but you're going to go through that discovery handout and you're going to notice that. All right, so when I was graphing this, I already knew before I started graphing that this was a rose petal and it's going to have 4 petals. So that's how I knew that it was going to start here, swing around, go up, go over here, and swing around to there. It's kind of like a spiral graph. I don't know if you know what a spiral graph is, but a spiral graph is an art game, an art toy, and it allows you with discs to make nice little spirals and stuff like that and make all kinds of interesting spiral graph pictures. All right, so that's just graphing polar equations, okay? You plot the points and you've got to figure out how to connect the dots together. So I can't emphasize enough how important the discovery handout is, that discovery sheet, so that you know when you look at a polar function, you already know, is this a limacon? Is this a lemniscate? Is this a cardioid? Or is it a rose? Okay, so if you already know the patterns, it'll make them so much easier to graph. All right, so there's your introduction on polar graphs and how to graph them. So where we're going from here is actually how to do calculus. How are we going to find tangent lines and curve length and area and all that? So we've got the calculus to do from all of this. But right now I want you to understand what polar curves are and how to graph them. So do that discovery handout and then do the practice problems. Let's see, I think they got the practice problems listed here. So on your practice problems, you're doing 1 to 39 odd. All right, 1 to 39 odd.